Alright, so here's chapter 16, the Milky Way galaxy, which of course is our galaxy. So we're going to start off with a little bit of historical perspective. I mean, humans have been able to see the Milky Way since, humans have been around. No one really knows, before telescopes, no one really knew what the Milky Way was. It was just kind of a cloudy-looking band across the sky, and it would always appear in the same locations. That is, it moved with the same way that the stars, moved, in one night. They move, of course, from east to west. That's just because the Earth is rotating from west to east. But this, this cloudy figure in the this cloudy thing called the Milky Way in the night sky moved with the stars, and so people really didn't know what it was. There was lots of mythological ideas in ancient human civilizations. Anyhow, of course, in 1609, Galileo builds a telescope and aims it at many, many different things within the solar system and then certainly outside of the solar system. And he, in fact, aimed his little primitive telescope at the Milky Way and found there were stars. That's what it is. It's just the stars are just too dim to see individually, and so you see this kind of swath of light in certain regions. And again, they exist in the same certain regions night after night, as the Earth goes around the sun. Different people contributed some different ideas, as it says here. Probably Herschel, who was an actual astronomer, had the most influence. And people certainly noticed the fact that the Milky Way, this swath of cloudy-looking light, was not evenly distributed in the night sky. It's not uniform everywhere, and therefore, people. In fact, Herschel, who was an English astronomer, actually made a very rough sketch. This was just raw data. This is just counting stars and representing these stars on a piece of paper. And this took him a long, long time. Roughly, if you just looked up with no binoculars or telescope or anything like that, you can see the human eye is sensitive to about several thousand stars. Anyhow, one of the things that Herschel did, and it's rather amusing today, is and it's certainly understandable today, is he put the Earth at the center, the Sun and the Earth at the center of the Milky Way. Well, it turns out that is completely incorrect, but he had no way of knowing that back then. Fast forward to the 20th century, and there was a guy named an American. There were other people too, but an American named Harlow Shapley actually determined that the Earth, the Sun and our Sun, of course, and the Earth were not anywhere near the center. In fact, they were about 2/3 of the way out. Now, how did he do that? Now, in the early part of the 20th century, there was some pretty large telescopes coming into existence. There's a famous Mount Wilson Observatory that had a 100-inch telescope. And then, of course, the Mount Palomar Observatory a little bit later of the 200-inch telescope. Anyhow, here's how Shapley determined this. Oops, excuse me. The way he did this was by basically he looked at stars where he could figure out the distance to the stars. He used variable stars, all over the galaxy, right? And he noticed that there were some variables that were actually inside of these spheres, these tiny spheres of stars, where these spheres can contain, like, hundreds of thousands of stars, or even up to several million stars. At any rate, he noticed that people called these regions globular clusters, and he noticed that these globular clusters were not evenly distributed across the sky. And using variable stars, he determined the distance to the globular clusters. And then he said, well, wait a second. The globular clusters seem to be surrounding a central region. It's not where the sun is, but it turned out to be about 2/3 of the distance from this central region. Our sun turned out to be about 2/3 of the distance between this central region, that is the region where all the globular clusters were in orbit around this point in space. Of course, nowadays we know that that's the center of our galaxy, but he didn't know that back then. And so this was the first rough approximation. Well, not really even rough approximation. This was actual measurement, figuring out our place in the Milky Way galaxy. So, and of course there was a problem with this right off the bat. Harlow Shapley did not know the difference between these RR Lyras and the Cepheid variables. These are, remember, the RR Lyra are the short period variables, and then the Cepheid variables are kind of medium range variable stars. And then remember, the Myra variables are the long range variables. So the fact that he didn't distinguish between these two made his numbers come out a little bit wrong, which is fine, right? There's much later people, and he also never made any corrections, as it says in this slide, for dust. The variable stars, their brightness was not truly indicated, because he didn't take into account the fact that really, really distant stars had to pass through a lot of dust in the Milky Way, and therefore their luminosity was not what he was recording. So all those kind of things have been corrected for, and continue to be corrected for, as we learn more and more about our place in the Milky Way galaxy. To this day, if you ask the average astronomer how big is the Milky Way, they will tell you it's about 100,000 light years from end to end. Now, we don't exactly know where the ends of the galaxy are. We know that the Milky Way is a spiral galaxy. So this picture right here is a top down. It's like looking at the north pole, if you will, of the Milky Way, and then looking down upon it. And you can see these spiral arms that are spiraling from the central bulge region, that is this area around here is typically called the disk of the galaxy. There's several parts that we want to get into. The disk of the galaxy has very high density of stars. So as it says right here, as you get closer and closer to the center of the Milky Way, you get millions of stars per cubic light year, and then you get further out, out towards the edges of the spiral arm. There's a lot fewer stars. So 0.003 stars per cubic light year. You're comparing that to right towards the center. An important part about the disk of our galaxy, the Milky Way galaxy, and by the way, we will be talking about other galaxies in the next chapter, but right now we're just going to concentrate on the Milky Way. Our galaxy has roughly 15% of its mass is composed of dust and gas. Is still composed of dust and gas. And that's important because later on we're going to find out that material has the potential to become new stars. And there are still new stars. There's stellar nurseries. Is part of the Milky Way galaxy. That's not going to be true in all galaxies. Just to keep that in mind. Keep that in the back of your mind. So that's the disk of the galaxy. Around the galaxy, so this is kind of an edge on. If you were looking at the Milky Way really, really far away, this is the disk, okay, right here, and then in the middle of the disk, extended out in 3 dimensions, is what's called the nuclear bulge, or the bulge area. That's in the heart of that is the center of our galaxy. Outside of the disk is a region called the halo, where the globular clusters exist. Those are these spheres of clusters of stars that range anywhere from hundreds of thousands of stars. So one of these globular clusters, we'll look into this in a little bit more detail soon, but one of these little clusters, or they're not really so very little, can have as many as hundreds of thousands up to several million stars. Not all clusters are the same. And another interesting thing about the halo, and we'll get into why we know this now, is that that is the region that contains dark matter. Right? You might have heard of dark matter before. We'll discuss exactly we don't know exactly what it is. We know it exists because of its gravitational influence on the galaxy. All right, so and there's the bulge itself. It takes up from one end of the bulge to the other. It's not completely spherical as it's shown here, but it's about 1/3 of the size of the galaxy. The diameter of the galaxy. So as far as the mass of the galaxy goes, this is actually more of a lower number. So if you added up all the mass of all the stars in the galaxy, it turns out actually it's kind of interesting, and we'll talk about this in more detail, but the stars in our galaxy, most of the stars are less massive than the sun, but there are stars that are more massive than the sun, certainly a lot more massive, and it turns out that the average of all those stars is about the mass of the sun. All right, so anyhow, the total mass of our galaxy is roughly 2 times 10 to the 12th, or 2 trillion times the mass of the sun. Okay, so that's we know that it has dark matter, and we'll talk about why we believe that, or what evidence that shows that. The lower end of the estimate of the number of stars in our galaxy is about 100 billion. There could be a lot more. There could be 150 million. 150 billion. Let's make sure that we're clear about that. It could even, I've even seen some published references that estimate that some of there could be even 200 billion stars. You can't count them. There's that many stars in the Milky Way. How old is the Milky Way? Some of the earlier estimates put it at about 15 billion. That's, of course, impossible because, well, a future chapter that we're going to get into, chapter 18, will deal with the Big Bang, and we know that the universe is only about 13.8 billion years old. Better estimates nowadays put the age of the Milky Way at about 13 billion years. So, roughly 8 billion years after the creation of the universe. There's of course, we try to do a stellar census, figuring out what types of stars there are in our